Okay, thank you for coming to the fourth day of the workshop. So we have Professor Yuki Yokokura from Kochi University of Technology. Is going to talk about evaporating black hole and quantum gravity phase.
Thank you for coming to my talk and good morning. And in this talk, I like discuss a basic question. What is a black hole? Yes. And of course, question. And this is still a question because still no one knows the correct answer yet. And theoretically, we have three theoretical problems. Of course. And the first one is the topic, and we are talking in this workshop, and the information problem. Yes. And the other and another problem is singularity. Yes. And the last one is, of course, the origin of area law. This one, yeah. And currently, in the world, and there are many approaches to understand these problems. But I think most ones are designed to tackle one of them only, not all ones. However, nature must allow us to have a solution to resolve all three, right? And this such a very strong constraint should be a key point to find a true picture of black hole in our universe. And of course, plus alpha, we have to be careful and observation. And gravitational wave, or currently as shadow we have, and such and observation data, and should give a strong constraint to such theory. So, and by this motivation, and in this talk, let's forget the classical picture. Of black hole. Forget, please. Okay. So, and in this talk, I don't define a black hole by existent horizon. Okay. And instead, we want to address this question. What is the definition of black hole in quantum mechanics, quantum theory? Yes. What is definition in quantum mechanics? And of course, such a question is very challenging. And but maybe one very naive definition is this one. Naive definition, and black hole defined compact object and formed by gravitational, I'm sorry, collapse due to quantum dynamics. Yes, this is quite naive idea, and we have some matter, collapsing matter. This collapse to something should be formed. And the point is here, and time evolution is governed by quantum theory. Dynamics of ideally gravity, ideally, and matter both. Yes, this is one idea.
Sorry, so you mean
Yes.
There's no other force besides gravity? Is that?
I'm sorry?
I mean, how do you distinguish this from ordinary star? Is it because there's only gravity, or?
Yes, and the point is here, compact. Maybe, and I should add the most compact. And such an object must be consistent with observation data. And from the object we are currently considering as black hole in the universe. And because and the current data and suggests such idea. No.
How do they know that from observation to define that the most compact object is black hole?
So, for example, and if you consider a neutron star, and such star cannot explain the data from the object we consider and the black hole now, right? In that sense. So, in this sense, this idea is quite a phenomenological definition. Okay.
I understand.
Yes.
So coming back to the question, I think that Professor Ho was asking, suppose you have a neutron star and you're considering its collapse to a black hole, right? So what forces are you considering in that neutron star model to get you to the black hole? Is it just gravity and some effective fluid description, or do you consider like nuclear forces and weak forces and other forces? That's, I mean, what's going into your model to turn it into a black hole?
I see.
In that diagram, which you've written, like matter going to gravity.
Yeah.
So what's the model, like what are your assumptions going into that matter model?
Okay, and indeed, and that is and today's topic, okay? And I will explain more explicitly and what happens if we follow this idea, okay? This is today's main topic, definition 1. And I proposed another definition. This is today's topic. And the definition 2 is this one, more fundamental in some sense. Black hole is defined as a configuration that maximize and some dynamic entropy for our given fixed surface area. Yes. And of course, and this definition is again, in some sense, phenomenological. And any object and eventually should collapse to a form, collapse to a black hole, right? And under a very strong gravitational limit. So, and such universal formation should correspond to second law, including dynamics of gravity eventually. And this fixed surface area, this constraint, of course, motivated by boost bound, something like that. Yes.
But don't fix the mass contained within that surface, then you can actually get more entropy than A by 4G. So I think you want to fix the surface area, but also the total energy available.
In the case, no, I don't think so. And if you consider and some spherical region with fixed surface area, and depending on equation of state of matter, for example, and how amount of energy can be contained in this region changes, right?
Yes.
So in this sense, and here, maximizes thermodynamic entropy, this condition strongly constraint the configuration. This is idea.
Yeah, so I just wanted to mention that that sounds very natural, but it's quite surprising that there is a simple counter example. I'll just mention it, but we can talk about it later. I don't want
Okay,
to
yeah,
stop
yeah,
your
yeah.
discussion.
Yeah.
But if you just take many small black holes in the same area that you drew, not one black hole, but many small ones, you will actually get more entropy because the area of lots of little balls is more than the area of the surrounding ball.
Ah, okay, I see. In that sense, okay.
In that
Thank you.
sense.
Okay. So, thank you. And today, and we don't discuss this point. And I like just give one reference: TU03900. Yes.
When you define the thermodynamical entropy, do you need to require the third law?
You need require
Third law.
second law. Yes.
Third law.
Yeah.
Also need third law?
Yeah.
But I remember that we have a black hole to find the third law.
You see, and actually, including dynamics of gravity, and as you mentioned, and second law, the notion of the second law is very subtle, and because in the system.
I not say third law.
Third law.
Yeah.
Oh, I'm sorry. Yes, and I don't. Yeah, I don't assume that one.
Yeah, I remember that if you have a correct case, some has mentioned proof that the third law can be violated. Yes.
Okay, but from my point of view, and most fundamental laws in thermodynamics is zeroth law, second law, and the first law. Yeah, three. Yes.
Okay.
Yeah.
So
Yeah.
may not need the third law.
I think so.
And here you define the black hole by the combination of the dimension 1 and dimension 2. Is right?
Originally, they are independent.
Okay.
Originally.
Okay,
Yes.
you want to show their equivalent?
Eventually, and in this paper, and according to this idea, and we can find the same picture as this one, eventually. But I'm sorry, I don't explain this point here. Okay?
Okay, thank you.
Yes, thank you. So, and let's go to and the basic idea of this one. Well, this one. Yes. Basic idea. Yes. And suppose, and we have black hole with quotation here, okay? And we throw a particle to this object from the outside. And we are standing here from a far point somewhere. A question, what will we see? And in the case of zero quantum effects, and of course, we have horizon. And at the horizon, redshift is infinity. So, and this ball particle just staying on the horizon forever, okay, from the outside point of view, okay? Now, let's consider quantum effects. And in this case, this is classical. In this case, we have Hawking radiation. Oh, I'm sorry. I should write here. Hawking radiation. This, and again, and from outside point of view, this particle should be around here, like this. But due to the time evolution, this one, black hole, shrink. Like this, yes. And this particle follow the shrinking black hole. And repeating this process, and then eventually, if black hole and evaporate completely, the particle comes out the opposite side without entering inside. Yes, this is quite naive picture. Oh. And the question is it possible to describe this time evolution or not? Let's make a simple model to test this thought experiment. Model. And this is R radius, and this is U. U is outgoing now time. And now, and this dot line is position of the shortest radius. I'm sorry, and in my talk, I use this notation. A is shortest radius, okay? And the same as Payman's notation, this one. And here, Hawking radiation exists like this. And this A is decreasing according to the Hawking radiation, but, you know, and this final stage is, of course, non-trivial, but for simplicity, here, assume, okay? And to describe this outside background geometry, and I use and outgoing biogeometric. Metric is given by like this. Yes, and now A is decreasing by Stefan Boltzmann law of Hawking temperature, like this. Sigma is just a constant, but, and it is proportional to this one, proportional to this one. And N is a number of degrees of freedom, contributing this Hawking radiation, okay? And of course, this h bar g is square of Planck length, okay? And in this background geometry, and the particle comes like this. And then after that, what happens? This is a question. And I denote position of a particle is R with index P, RP, okay? And for RP close to the decreasing shortest radius, and the equation motion of the particle is just given by null geodesic equation, like this. like this. And the point is here, AU is decreasing, determined by this evolution equation. Yes.
This is a postulate, or this is just something we see from the classical geometry?
This one?
Yeah.
If you use Hamilton-Jacobi equation
Yes.
for a particle with any mass or any angular momentum, and if you consider this case,
Yes.
eventually Hamilton-Jacobi equation universally gives this equation.
So, okay, so let me just clarify, because I'm just confused about how this happened. If I use the Eddington-Finkelstein type coordinates you wrote there, and I take a small back reaction, so black hole is evaporating like in the usual case.
Yes.
Then normally the trajectory of an ingoing null photon, let's say coming inside, it does go inside the horizon, even though the horizon is shrinking. So in the normal picture, I think that doesn't happen. So I was wondering if you added some new physics assumption to make it that it slows down. It doesn't cross the horizon.
Yeah, here and so far, and I don't put any new physics.
Okay.
And I just use this simple model to describe evaporating black hole geometry. That's it. I don't put any new physics so far.
So if the black hole is not evaporating, this equation still remains the same, right? The A of A will just become
the constant.
Yes, constant.
Yes. So in this sense, this story is strongly depending on the assumption that black hole evaporates by this law.
Yeah, so I guess I'm just a little confused between what is U and what is V, because I think
U and V?
Yeah, so if you write dRp by dV, the other
yes.
Will it go inside the horizon then?
In that case, you are saying like this, right? Yeah.
Because you can use either coordinate, right? You can use U and R or V and R. If I use the other coordinates, will I see the particle go inside the horizon?
Yeah, you're right.
Okay, so I think I was just confused about U and
Yeah. And from now you will see. And the point is, and we have to consider time evolution of the both evolution of this particle and time evolution of this shrinking to effect at the same coordinate, right? This is the point. However, if you use ingoing null coordinate, and then by construction, and the infolding particle is just described by V constant line, right? So you cannot consider the Borst effect at the same time coordinate. So you cannot compare and the two evolution. So I want to avoid such point. So now I'm using U coordinate and to follow the Borst time evolution, this evolution Borst, and at the same time coordinate. This is the point. Okay, thank you.
I think the point is that if you use ingoing Vieira metric with, say, V-dependent A, it's a completely different solution from this one. I mean, here you have A depending on U in the outgoing Vieira metric. That means you have continuous outgoing energy flux coming out directly from the horizon. So, but if you use ingoing Vieira metric with a V-dependent A, then actually there is no outgoing energy flux, but there is an ingoing negative energy flux.
Yeah.
Horizon.
Yeah.
So it's a two different
Yes. Sorry?
It's just free flow geodesics, right?
Yeah, this is just a geodesic equation. Yes. This is just a geodesic equation, not geodesic equation. It is. And from now, and we want to solve this equation. And the point is this condition. We are now interested in this case, right? So we set this way, like this. And delta R is much smaller A, like this. And then this equation becomes just a substitute here, and the A du, the delta R du, minus, and delta R, and 2A plus delta R, like this. But, and approximately, we can get this one. And that is our equation motion is this one. This one, okay? And now, and we have this equation for A, and so it is just this one, right? The point is here, it is, this first term is, of course, negative. This negative represents and falling effect, right? And without this one, and delta R gives you and just exponential approaching effect. And in that case, and you get just this case, right? Exponentially just approaching here, and forever the particle cannot enter it here, right? Of course, classical case. But we have this small second term. It is positive. This is evaporation effect. Evaporation effect. As you can see, and this negative term, this positive term can be balanced for delta R close to this order. Eventually, these two terms balance. That gives you delta R approaches to just 2A square, so A over 2 sigma here, yeah. And equivalently, that means RP close to A plus A2 sigma. This is outside A, right? So the answer is this one. This guy is approaches and but doesn't enter here. And zoom in around here, and particle is here. This is just a horizontal line, and I'm sorry, I should this one, and this is decreasing shortest radius, and this is approaching particle. And between two, and always this distance exists, this one. And actually, it is equivalent to this distance as a proper radius, proper. And as order, this is this one, like this. If N is sufficiently large, for example, N is order, for example, just an example, 1,000, something like that, and then it is sufficiently large compared to Planck length. In this sense, and the particle cannot enter AU, inside AU, without a coordinate singularity, okay? So, and this simple analysis and gives interesting naive time evolution of crops. And we have, again, a spherical crop in matter, like this. Like this. And this is spherical by assumption. Approximately, and we can regard this object as many thin shells. Approximately many shells. Now, let's pick up just one ice shell. Pick up. And zoom in like this. And the position of the ice shell denoted Ri. And around here, and the coordinate is Ui and R. And again, if this the shortest radius corresponds to the quasi-local energy inside this Ri, Mi, I denote. This guy, if decreasing like this, again, if, and then this Ri approaches to this asymptotic position eventually. In terms of this local time coordinate Ui, that means this collapsing object just shrink, without forming trapped region. Just shrink. Some compact object. A horizonless object form. And by assumption, this one emits the Hawking radiation, and then maybe eventually completely evaporate. This is a naive time evolution based on this analysis. Okay. But, and maybe, and you are thinking, whether or not this is true mathematically, right? So I will show this is true from now. Yes.
One of the big assumptions here is that you assume that each shell follows the same evolution equation.
Yes, that one. Yeah, if
Okay.
that part. Yes. Yeah.
Yeah, so is in this multi-shell picture, is Hawking radiation assumed a priori, or is it still consistent with there being this multi-shell object emitting Hawking radiation, even though it's horizonless?
Sorry, what is your question? I'm
Yeah,
sorry.
so you assume from the beginning that you have Hawking radiation.
Yes.
And that helps you justify this multi-shell collapse picture. But this picture, does it justify, is it self-consistent with the existence of Hawking radiation? Because now you said that that's a horizonless compact object. So
And from now, I can show, and that assumption can be justified self-consistently. Yes. So, and to show this is a case, and we use this equation. This one, yeah. And it is so-called and the semi-classical Einstein equation. Yes, this one. And as you know, and here, and the G mu nu is classical, but and the matter field is a quantum. Yes, quantum. And this guy is called the renormalized energy momentum tensor. And the point is, and this is 4D. Yes, this is a key.
So in all of this, you're basically making a linearized assumption for the evolution of R. Isn't this right? Like this, when you're writing R going to A plus 2 sigma over A, there's a linearization which is going on because in your derivation, you've suppressed this denominator of A plus delta R. And so that's how you end up with this linearized approximation.
No. And if you like, and you can just directly solve that original nonlinear equation by numeric technique. And you can check this one.
So
explicitly, if you like.
So you'll get the same answer?
Yes, of course. And so in that sense, linearization is not important here. Just here, to demonstrate for you in an easy way, I just use linearization. The essence is not linearization, right? Okay. The essence is including, I'm sorry, this evolution, both. This is a key. This is a key. Yeah.
Okay.
Yeah. Thank you for your point. Thank you.
Okay.
Yes.
I have another question. So, following the host question previously, so usually when we calculate effective argument tensor in this system, the flux near the horizon is usually not outgoing, but rather a negative ingoing flux, right? So, how do you remedy this kind of a classical picture?
I'm sorry, and from now I will explain that point. Okay. Please follow me, okay?
Okay.
Thank you. Yes. Yeah. And yes, and the point is how to solve this equation. This is a key idea in my theory. And we solve this is self-consistent way. Consistent way. And the first step one, set candidate metric. First, at this stage, we just set candidate metric here, okay? At this stage, we cannot claim that this is a solution of this one. We cannot, okay? So here, just a candidate, okay? I want to stress here. And next, step 2. Set candidate state. Again, and this is just a candidate, okay? And step 3. Let's calculate renormalize energy momentum tensor by using this one and this one. As you know, technically, it is very, very hard, right? And finally, let's set self-consistent equation. I mean, this one. Here, this renormalized energy momentum tensor gives you right-hand side. This candidate metric, of course, gives you Einstein tensor. The question is, can you solve this equality in a consistent way? If yes, story is closes self-consistently. Okay, go ahead. I'm sorry? This one?
Because in the step 4, you write mu nu. So what's the difference between mu nu and if you change T times? It's just T times for God
This one. Yeah, I'm sorry. And sometimes I don't write this way. Okay. Yes, I'm sorry. Yes. Yeah. Yes, right. So, and by using your brain effectively, and please guess nice candidate metric first, right? And then you can also guess and candidate state. But as you can guess, usually it is very difficult. Okay, but already we have this naive time evolution picture we have. So, and let's use this view and make a nice model for this candidate metric. Let's go. Okay. Good. Okay. And candidate metric. And first, I want to stress that, the candidate metric we are going to have from now can be derived in many ways. And here, I just give you one method to obtain this one. So, okay. And simple derivation is given by this reference, 1701 03 455. Okay. And before going to main story for candidate metric, and I like prelude and pre-argument supports thin null shell collapses and evaporate. Okay. Pre-discussion. And the picture is quite simple. And this is just a thin shell, right? And it is collapsing. But according to my assumption here, just assumption, okay? Be careful. And during the collapse, and radiation is also emitting, okay? So, of course, here outside is visor, but inside is flat due to Birkhoff theorem, right? So, shrinking, but evaporating, and eventually like this. And we don't care about this evolution is dynamically true or not. We don't care here, okay? And just I want to describe this setup geometrically like this. Yeah, this is flat, and this is a visor. So, and so we can, this metric, for the outside region, in this way. And the position of the shell is just R shell. And and the outside R shell. Yeah. And R inside is flat. So let's use different time coordinate capital U. Like this, yes. Here, and I want to show to you is how to connect these two metric along geodesic line of null shell. It is quite simple. Just you set this part equal to 0, this part equal to 0 on article R shell here, yes? And then you can connect two time coordinates, small u and large u. Let's do it, okay? I mean, just 1 over RAU du equal to minus dRs equal to du. Like this. We have two equations, right? And the first one comes from that one, and the second one is comes, I'm sorry, and this one, okay? Like this. And from here, we have this equation. I'm sorry, here. Be careful here. RS, AU. So this one. And another one is, again, here, a geodesic equation for shell motion. Here, okay? So, and we know by assumption, form of AU, right? We know. So, and from this geodesic equation, you can get functional form, RSU. And now, and plugging here, and then you can get relation between small u and large u. So in this way, and we can complete the set completely and set up the coordinate system like this. Of course, except for around here, right? Final stage. Now, this is just a pre-discussion. And let's go to the main discussion, right? Main discussion. And the idea is this one, that one, right? So, and we regard spherical collapsing matter as many thin shells like that. Let's model that guy like this. One shell, two shell, like this, right? And many shells is coming. Oh, it's a little bit difficult to write. Here, yes. And this is R1, Ri minus 1, Ri. And the outermost is R small n, like this. And R is the position of the ith shell, like this. And of course, and to each shell has its own decreasing shell radius, like this. A0, A1, blah, 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 and AI, AN, like this, of course, okay? And the model is this one. Just above ith shell is described by ith bigeometric. I'm sorry, like this. Yeah, of course, then the bottom part is flat again. Let's use again capital U. And outermost is just a standard, I mean, without index, bigeometric. Like this, yes. Recursively, okay? And now, let's keep that one. And now, as we have done, like here, we have to connect many time coordinate system. U1, U2, blah, 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 UN, in a similar way. So the equation is again like this. I'm sorry, I dropped coordinate the UI, okay? And the RI, AI minus, and the DUI minus 1, like this. And the equation is for 1, 2, up to n. Yes. We have a complicated coupled equation system. This one. And but for later calculation, let's write this one in this way. Here in the numerator, AI minus AI minus 1 means the energy of ith shell. If you divide by 2g, right? This corresponds to energy of the ith shell, like this. So in this way, and this equation has backreaction effect from the ith shell energy, okay? And now, we will solve this system for continuum limit in this sense. Continuum limit. Yes.
So when you say you have the back reaction included in these equations, do you mean the back reaction from the classical energy of the shell?
Yes, in that sense here.
But not yet the back reaction of the stress tensor of Hawking radiation.
From now. Not yet.
Not yet. But you will put it later.
Next page, I will explain. Next page, I'm sorry. Yes, just a moment. Yes. Here, okay? So, and now, okay. And to solve this complicated system, and we set this assumption, ansatz. Is this one. Again, this one, ansatz. Here. So as long as we have this one and the back reaction of the Hawking radiation is introduced in this system, as long as, right? But of course, this is just the ansatz. At this stage, I don't claim yet it is a solution. Okay, please be careful my logic, right? In this part, I just trying to construct just a candidate metric at this stage, okay? And according to this ansatz, I'm sorry, I erased. And we already shown ice shell can approach to here. Now, and we already this condition for any I. Yes, this is ansatz. Okay. And using these two ansatz in this continuum limit, we can solve that coupled equation I will show. And for simplicity, and let's introduce this notation Xi. And from here, we calculate just a recursive equation like this. Yes. I'm sorry. Opposite minus. Yes, minus. Yes. And then the minus log, we have that one, right? So let's use it. Ri minus ai delta ai, like this, okay? And now, and we assume delta ai is small in this limit. So let's expand like this. And here, Ri minus ai now satisfy this condition. So let's use this one. So we have 2 sigma ai. And what is delta ai? Delta ai is ai minus 1, like this. And now, under that assumption, delta ai is sufficiently small. In this assumption, the first factor, ai, can be right like this. ai plus ai mean of this one, right? Right. So we have, under this assumption, we have minus 4 sigma ai square minus ai minus square, like this. And now, and let's use initial condition. Initial condition means, and yeah, here. In this picture here, and the bottom, and U0 corresponds to just a capital U. So that means Xi0 is 0. And of course, and A0 is flat, so 0, right? So using this initial condition in the collapsing evolution, that means you have Xi is minus ai square for sigma, this one. We have solution, okay? Sigma is positive.
Yes.
Yes, and by the physical condition, I mean, so sigma originally represents intensity of Hawking radiation, so it should be positive.
Okay. Yes. But for your solution, you do not need that.
I'm sorry?
For your solution, you do not need to require that.
Right.
Okay.
But I'm sorry. No. Here, to justify this argument, this must be larger than AI. In this sense, sigma should be positive. Thank you. Thank you for your point.
Thank you.
Yes. Yes.
So I just have a very simple question. Like, if you have a sequence of shells, why aren't they interacting with one another? Like, are you ignoring that interaction? Like,
the point is, this system is spherically-symmetric. And so the inside and the evolution is not influenced by the outside evolution.
So it's purely spherically symmetric throughout.
Yes, here, yes.
Okay. And so these corrections do not affect that spherical symmetry. It remains spherically symmetric throughout. Like it's a spherically symmetric collapse throughout. There's no corrections which will change it, is what you're saying.
You mean that if I consider a non-spherical symmetric cases?
No, I'm saying as you add corrections, let's say you have anomalies or you have any kinds of corrections which you would add to the system.
Sorry, what do you mean by anomaly?
You'd eventually consider quantum matter, you're saying, with an expectation.
Thank you. And actually, and the anomaly is a key guy in my story. And later you will see, anomaly appears.
So those would be like perturbative effects, which would correct your assumption. And at that point, those.
So at this stage, I don't consider effect of the anomaly here. But, and self-consistently, anomaly effect is automatically introduced here eventually.
Okay.
Yes.
So
but I'm sorry, at this stage, I mean, in constructing process, I'm sorry, I cannot input explicitly anomaly. But taking the continuum limit and to get the candidate metric, you can find an anomaly effect self-consistently. You will see later. Okay. Thank you. Yes. Okay, now, and from now, and we can finish this section, candidate metric. Good. And focus on the shell that passes a point you are. Capital U, small u, and in this sense, okay? And suppose such shell corresponds to just Ri, okay? And we want to evaluate metric in and make metric. The metric around here, and in this limit, continuum limit. Okay, and around here, originally, it is just a ith bigeometric in this sense. Okay. Now, and here, R minus AI over R, this factor can be written like this. Because the point R we are focusing on is close to Ri in this way. And here, and the numerator, Ri minus AI, satisfy here, yes, this condition. So, and we can set to sigma AI Ri like this. But this, you can see, and this subleading term, this second term is much smaller than the first term, as long as AI is larger than Planck, larger than Planck, as long as. So you can approximate again like this. And then let's use the same argument, this one. And similarly, and you calculate here, dui. And du is, du is dui, du. And what is this? This one, that is given, I'm sorry. I missed the index ui. Maybe, and you notice here. I'm sorry. And from here, from this definition, and you get exponential minus xi, like this. The what is xi? We have the solution here, box. And that is, and the exponential 4 sigma ai square du. And again, ai close to ri, ri close to just r. So this gives you 4 sigma r squared du, like this. So in this way, and we get the candidate metric. So in substituting these two results to that one, we get this one. Yes. This one. The point is, this is static. This is static. Even though the system itself is evaporating, right? And you can see how to fill the gap between this static condition and evaporation condition in this way. And just, I mean, you can connect this metric to isometric, and by using this one for un, xn. Xn means, I'm sorry, I want to connect this capital U, which is coordinated in the bottom, in the flat region, and to and connect this one to outside coordinate, time coordinate, small u. And it is just exponential minus xn, I mean minus and 4 sigma and a without index a square, I'm sorry, square, like this. And but, and total size is, of course, again, given by like this. And you can, taking the square, you can neglect this guy, like this, approximation. So, like this. And substituting here, and you get a time-dependent version of the metric, which is the metric from the outside observer. This one. This one. Yes. And physically, this one represents interior of dense region. Here. This one. Interior metric here. And but, and be careful, as you can see, if you take naive limit to r equal to 0, and this the metric breaks down, of course. But here, we assumed and this Hawking radiation condition for each I. That means here, AI must be and much larger than Planck. So this metric holds only some lower bound between lower bound and the surface. And the lower bound must be like this, yes. And here R0. And this is the surface of the object. And it is emitted. And the outside is just a standard visor. Standard visor here. This is outside, yes. And of course, this final part is unknown. And the inside here is still unknown, yes. Yes. This is a one candidate metric. Yeah. And here in the I like mention one point. This one, sigma, originally proportional to n h bar g. So you cannot take h bar 0 limit. You cannot. Cannot take h bar 0 limit. I'm sorry?
Why wouldn't you take n to infinity and h to 0? Like you can have a double scaling kind of situation, which you can consider.
I'm sorry, I don't understand
You can have a double scaling scenario where you could have n going large and h going to a small value.
N is large and
G going to 0.
G equal to 0. Oh.
So sigma held fixed.
I see. I'm sorry, and so far I haven't considered that case. What happens? Yeah, thank you. Yes, okay. Oh, okay. And before finishing this section, and before going to the break, and I want to give a more generalized version of that. And so far, and sorry. Just a moment. That static equation, that static metric, of course, can be described by the stationary case. Stationary case. I mean, just a evaporating guy move to heat bath, and then system, of course, stationary at Hawking temperature, like this. This is a physical situation. But the point is, this one here, strong redshift. And thanks to this strong redshift, and interior structure doesn't change drastically during the time scale of the evaporation, m to the cube. So in this stationary case, interior metric is the same. And you can write metric like this. And for the inside is just let's use Schwarzschild coordinate. I'm sorry. Like this. And for outside, approximately, and constant, this A is a constant. A is constant, this case. This one, yeah. I'm sorry. And here is some numerical factor is here. But I just wanted factor is, let's see. Yeah, here too, like this. This is a case, yes. Okay. This, like this. This is a stationary case. And you can just change a time coordinate from U to just a T, like this. Yeah. This is inside, this is outside. And generalize. Generalize means this one. And so far, emitted Hawking radiation comes out without scattering. I mean, suppose radiation come out from ice shell, but above it, and many shells exist. The original my argument, we don't consider a scattering effect. Scattering, no scattering. So, and 100% emitted radiation go out smoothly. But physically should be these two interact, right? So let's model this effect. And some part emitted, but some part comes back, scattered back, right? Yeah. So, and to model this scattering effects, I introduce phenomenological parameter eta in this way. And I'm sorry, I don't introduce explicitly definition of the coordinate, but you can understand. U coordinate, a capital U, UV coordinate, right? Just a light cone coordinate, UV. And UU corresponds to just this guy. And UV is this one. So, and the ratio is setting like this by using phenomenological parameter eta. So this case, eta equal to 1 without no scattering, but eta equal larger than 1, and scattering is introduced. And then, in terms of TR coordinate, and you can get nice expression. This one. This is a diagonal RR. This is diagonal TT. I mean, it is a kind of equation of state. So, in a macroscopic sense, eta plays a role of a parameter of this equation of state. Eta equal 1, gives you just a pressure, radial pressure equal to energy density. So, as you can see, and just radiation propagate without scattering. But if you have some finite effect of the scattering, and equation of state behaves like a massive object, right? Massive fluid. Yeah. So that condition is equivalent to this one under that coordinate dr. Yeah. Yes. You can check. Yes. Anyway, I'm sorry. And if T mu equal to G mu, and then you can generalize that metric is like this. I'm sorry. This is the candidate metric we will discuss from now. This one. This is the final form. This one. And R is A plus 2A sigma A square. Yes, like this. This one. And eta take this range. And eta equal 1 is corresponds to scattering limit, and eta equal to corresponds to and zero pressure. Yes, like this. Yeah. Yes.
Theta, theta, and T phi phi. You need those stress tensors also, right?
After taking a break time,
Okay.
and I will. Thank you. Yes, yes. And this metric is given by me and Kawai-san. 2014, and reference 409. First, this paper gave this metric first. And I don't have a nice name of this metric, but and my collaborator just call it a KY metric. So here, and I'm sorry, and I use this name, just KY metric. Okay. Yes. Okay, take a break. Okay, and before going to the evaluation of the renormalized energy momentum tensor, and to answer the question by Matteo, and I like explain a little bit geometric property of this guy. And energy density behaves like this. Plus, of course, collection, but, and we only consider this case. So, and this correction is not important in my story. And RR is, I said, like this. And the pressure in angular direction is constant, like this. This is quite important. And plus, of course, correction, subreading correction, like this. And this is order of this one. And this pressure is a non-perturbative effect, and it is quite huge, and compared to standard pressure, this radial pressure. This large pressure and is important to support the system in this way. And system is spherically-symmetric, and this tangential pressure, let's denote P theta, right? And this tangential pressure and work are external force to the R direction divided by multiplied by geometric factor 2 over R. P theta, like this. This one indeed works to balance self-gravity. And then the system is stabilized. And you can check these facts directly to see and the TOV equation. And this large pressure can break so-called Budal limit. Yes. Yeah, and so we can make such a we can make the object so compact. Yes, but big question is why can we have such a large quantum pressure? Right, this is a big problem. Yeah, here you see this is non-perturbative pressure, and if you consider, for example, and just a 2D model or S-wave approximation, and usually you don't have such a large pressure, but here we have. So why or how can we justify such large pressure? I will explain from now, okay? Yes. And to evaluate renormalize the energy momentum tensor, and first, we have to fix some theory. And here, we consider, for simplicity, n massless scalar field. Yes. And phi A is 1, 2, n. Yes, okay. And scalar field. And first, I will explain procedure. One, consider the classical behavior. Of phi A, you see? And this step is quite important to get proper candidate metric. Find sorry, candidate state, I'm sorry. Yes. Okay. And this examination should lead to nice input to find nice candidate state. And next, let's solve Heisenberg equation in this background geometry. Yes. And fourth step, and evaluate regularized energy momentum tensor by some regularization process here, and I use in dimensional regularization. Here, I use dimensional regularization. And find, renormalize this guy. And by introducing, of course, covariant counter terms. However, you have to be careful with by including finite renormalization effect. This should be important, finite renormalization. And when you calculate some scattering amplitude, and you have always an ambiguity in the finite renormalization effect, similar here, right? So, and finally, and let's solve self-consistent equation. This one, okay? This is a procedure we want to do from now. And maybe for specialists, and I like write down explicitly the form of renormalized energy momentum tensor in the dimension regularization. This is the form. And dimension is 4 plus epsilon, okay? And minus epsilon psi mu is a renormalization point. Renormalization energy scale, right? And in the case of n scalar field, and you can use this counter term. And h mu nu is tensor comes from R square in the gravity action. And the k mu nu is square of our Leach tensor. And the j mu nu is from Kretschmann, okay? And alpha mu, beta mu, gamma mu is London complete constant. And for example, in the case of the alpha, and the expressed form is something like this. Like this. And the beta, gamma, blah, blah, okay? I'm sorry, and I should write and the reference for this evaluation part, and 2002 and 10331. Okay. Yes. Okay. And let's do step 1. And to do that, I should write here. Okay. Oh, sure. Be careful. Here, from step 1 to 5, we don't use Einstein equation. Okay, we don't use. And just this ky metric is just a background. Okay, just background. Okay, and so in this background geometry, and we will do this procedure. Okay, and then in the final step, step 6, and we impose that dynamic equation, and what happens? Okay, and step 1, and let's examine classically this equation of motion, classical analysis. Okay, and here let's take standard ansatz like this. Okay, and this triangle equation becomes something like this, and the potential is quite interesting. The case of large angular momentum behaves like this in a metric. And the surface of the object is here. And here is interior part, here is outside part, and it is given by the, and of course, Schur metric. And as you can see, this this classical equation corresponds to equal to 0 Schrödinger equation, right? So, and the physical mode is living on energy equal to 0, right? But you see, and the outside part here, but the inside part is here. The part I colored is allowed physically in a classical level, okay? So the point is, inside part is bound mode, only allowed bound modes. This is a case, and for angular momentum is large. And on the other hand, L equal to 0, S wave, and S wave can enter the inside and comes back to the outside like this. So S wave is in some sense is called continuum S wave in this way. But we can check how much energy is involved by this excitation, one mode excitation. It is given by this one. Planck mass over and the square root of n. This energy scale is much, much larger than typical fluctuation or energy scale in black hole, right? Much, much larger. That means typically not so many mode can be excited. This is a suggestion by classical analysis. Yes?
Do you have to worry about the boundary condition at near r equals 0?
No, and because r equal to 0 is regular in the metric, like that.
But you said your metric only holds.
Thank you so much. Thank you so much. Yes, you're right. Yes, you're right. Thank you. Thank you. Center region is assumed flat for simplicity here. Yes. Flat around the center. Yes, by assumption. Yes, and this assumption should be possible because, and you can check Misner-Sharp energy. Misner-Sharp energy. M r close to Planck length is order MP. Yes, we can check. I mean, you see, in the Misner-Sharp energy means quasar local energy inside radius r, right? So, and my metric can be applied up to and around here, right? So, applying the metric, and we can evaluate like this. That means the unknown center core should have at most such a small mass. So it should be not so dangerous to assume like this. So, but here, this is just a working hypothesis, right, at this stage, okay? So, and motivated by that argument, not so many modes can be excited inside. So it should be natural. Should be natural to take the ground state. Ground state 0 in ky metric. Ky 0. I mean, the 0 is simply defined like this. Expand the field operator. And of course, UI satisfy this Klein order equation. And here, 0 is defined by This one. So we take this ground state as the candidate state here, just a candidate state. Candidate. And 3, and we can solve and this equation. I mean, this field equation in the background of the ky metric, and by 1 over r expansion. Expansion. 1 over r perturbation, perturbation. R is large, and I'm sorry, and I don't explain the detail of this one, and but first I should say this is I'm sorry, the same notation, capital R, but this R is a rich scalar. Rich scalar. Ky metric and has this rich scalar. And L is this one. Capital L is given by like this. Factor 2. I'm sorry, factor 2. Yes. Yes. And as you can see, it is ADS2 cross S2, right? But this is a warped product structure, right? Warped product. Warped product of ADS2, S2, and S2. Yes. And but ADS radius is quite small, Planck scale, close to Planck scale. And the S2 radius is standard R, okay? So we have large gap between these two, like this. It is small. Thanks to this structure, and we can perform 1 over R expansion at each point inside R. And then we can solve this field equation perturbatively. And as a result, I want to keep this one. As a result, and we have 0th order, 1st order, blah, 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 blah. This is a solution. And this index is so strange. Here, okay. And using this solution, we can do step 4 and step 5. Step 4 and step 5. And I mean, renormalize energy momentum tensor given by 0th order plus 1st order 1, 1. Like this. And as a value, this 0th guy is constant R to 0, right? And this one is order like this, behaves like this. And the expression is quite complicated. And finally, and let's equate. This one, renormalized energy momentum tensor. Equate. Yes. And the key component, of course, mu nu, it has 3 independent component, TT, RR, theta, theta, right? three components. Okay, and we have whole components in this renormalized Einstein equation, renormalized energy momentum tensor. Sorry. So and the most important one is trace part. It is quite important. I can show explicit value, and this left-hand side is given by this one. And the right-hand side is h bar n this one. This one. This is the self-consistent equation for sigma. And this gives you self-consistent value sigma like this. This one. This is a solution. And another component, TT equal to TT, gives you and some constraint for renormalization coefficient. Some number, and eta is no. Like this. This is the self-consistent value of eta. Yes?
The trace equation, that relations between sigma and h bar or those degrees of freedom, is that exact or perturbative?
This is not, you see, yes, here. And as I said, I use this expansion.
Yes.
So, and this value is just a zeroth order.
So leading order. Okay.
This is zeroth order.
Thanks.
Yes, thank you. Zeroth order. Yeah.
So actually, I just want to clarify. So that's really a Planck scale energy density near the horizon, right?
Near, no, inside it.
Inside.
Yes, you see, and in my talk, I and describes that inside the black hole-like black hole object, and which guy doesn't have a horizon from the beginning.
Yeah.
And now I am proving the object can exist self-consistently. Can you follow?
Okay. But but you're going to derive this stress tensor from the stress tensor of a scalar field in some particular geometry. That's what we are supposed to do. We take the scalar field, we compute the
Yes.
normalized stress tensor in some geometry.
Massless scalar fields. Yes, yes. Now, yeah, I'm considering n massless scalar fields. Yes.
Yeah, n massless.
Yeah, yeah, yeah.
And so the standard stress tensor for n massless scalar fields in this metric has this kind of a very strong
Yes,
energy density. That's what you're saying.
yes, that is that one. That
Okay.
one.
And
Yeah, 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 yeah. Yes, and the point is this step here for the full for the fluctuation is important. I mean, taking the this expectation value, you calculate summing up L and M omega both, right? In this way. So, and if you consider only S wave or 2D model, you only have this one integration. But we have three integration here. So this full 4D fluctuation gives you order one contribution. This large contribution is this one. Actually, I want to stress here. This one agrees with anomaly, 4D wire anomaly. Explicitly. Yes. By applying this KY metric. Yeah. Anomaly. So, and finally,
Sorry,
and this,
can I,
yes, go
can I
ahead.
say that you have a black hole out of vacuum? You have, this is vacuum state, right? So it's like you have a gravitational.
Be careful. And my vacuum state is quite non-trivial because, and the background is not part of the background, right? Yes, yeah, yes.
But so the energy of the black hole comes from the vacuum
Vacuum
state in
fluctuations.
this
Yes, exactly.
non-trivial-
Yes,
okay.
yes, yes, yes. Thank you. Yes. So, and we already use and the two equation, mu trace and TT, and we can show then RR is satisfied automatically. For this value, this value, this value, automatically, yes. So in this way, and we have proven this one is holds self-consistently, non-perturbatively. Yes?
The G theta theta component is the next to leading order.
No. G theta theta. Okay. And I will show. And okay, thank you. And I will explain how to get G theta T theta theta. Yes, and the T theta theta is just a part of a trace part. I mean, TT by definition are T theta theta like this. But we know it is order R minus 2, and it is order 1. So this guy is negligible compared to this one. So, and physically, theta theta comes from anomaly. Anomaly. Yes, anomaly. Yes. Yeah. And how about Hawking radiation? How can we get Hawking radiation in this picture? And again, anomaly produces Hawking radiation. Yeah. And you can see this point by using this conservation law as a operator identity. I mean, in our case, it is described like this. Here, for simplicity, I'm using light cone coordinate, this one, capital UV, and this is conformal factor, and no. Like this. This is an energy momentum conservation law. And you see, and if you define tau AB like this, 4 pi r squared multiply 4-dimensional energy momentum tensor, this bracket part corresponds to 2-dimensional energy momentum conservation, right? This part is 2D part. But as you can see, this dynamics is full 4-dimensional. So, and the deviation from 2D dynamics, this guy plays a role of source term, right? Source term. So, and I'm sorry, I don't have enough time, so I will skip the detail. But we already shown this condition. And under this condition, first, we can see this yellow part automatically 0. Yes. And as a result, this equal to this, right? And intuitively, as I said, UU component corresponds to Hawking radiation. That Hawking radiation is produced at each point R by anomaly fluctuation. Yes. So this and the anomaly fluctuation generates a Hawking radiation at each point, and accumulating this effect in this line, and then eventually, outside is just a Baija, and here is dense region. So due to the energy conservation, final emission continuously propagate to the outside. This is Hawking radiation. So in this way, my mechanism to get Hawking radiation is quite different from standard Hawking radiation. The point is, and the point where radiation occurs is not vacuum, right? Instead, it has large energy momentum tensor, and it is a result of the matter and quantum fluctuation both. So, and naturally emitted radiation should contain some physical information from initial collapsing matter. This is a naive expectation, right? Okay, and let me finish my talk. But before that, I should say the meaning of this object. And this first meaning 0. And the first and the 0, this vacuum or ground state, this is the ground state. Oh no, I'm sorry. I already I erased. Okay. And the 0 is background independent ground state. Of the black hole. This is the physical meaning, you see? And we have shown, and this 0 state satisfy this equation self-consistently, non-perturbatively, right? And originally, and in the stage of where, and we are trying to find candidate state 0, we considered metric as a background, right? From first. But eventually, we have shown this 0 satisfy this equation non-perturbatively, self-consistently. That means notion of this state is state independent, background independent, right? And the physical view is like this. And the 0, many quantum fluctuation, and in 0 state, itself construct geometry itself. Yes. So in this sense, this 0 state is geometric realization. Instead, opposite, I'm sorry. And the G mu ky is geometric realization of this one. Yes. So in this sense, it is a background independent state. Yes.
When you say the background independent ground state, do you mean that you have a formula and it can be applied to any background, but the results still depend on background? I just don't understand what is the background independent ground state, because we know that the G mu at the left hand side, the G mu nu is a background. So in this sense, I should have something depend on the background. So what do you mean for the background independent ground state?
You see, and the state itself, usually in a standard semi-classical argument or in a standard QFT in curved space-time, and first we fix background, and on the background you discuss quantum fields, right? And in some state, right? Mm-hmm. The state is fixed on the background geometry, right?
Yes.
But here, we have shown this guy satisfies this dynamical equation non-perturbatively, right? So you see, from the beginning, Einstein equation itself background independent dynamical equation, right? Similarly, and this zero satisfy this dynamical background background independent dynamical equation non-perturbatively, right? So from the beginning, this guy doesn't have background. Rather, and this zero itself produce geometry.
But
Yes.
even if you just consider the non-perturbatively, but it still can depend on background. It's right? If, for example, I consider a gravity theory with a matter, then I treat the non-perturbatively from the matter. So in this sense, I can say, even if I prove that it's valid for non-perturbative sense, but the ground state is still maybe just valid for some background.
I see. Okay. And okay, for your question, and I would say, and my curvature scale is this one, right? And on the other hand, generically, this scale, in this scale, and notion of the geometry becomes fragile, right, usually. And for example, if you consider and graviton propagation, right, and adding n-loop matter effects, right, and that guy gives you this is bare Planck mass, something like this. I'm sorry. N times lambda square, like this. N is the number of the species, and the lambda is cutoff momentum scale, right? So motivated by naturalness, this should be this observed mass scale, right? And that means cutoff scale, something like this. But physically, it is, we have to be careful physically. I mean, of course, by definition, this is 1. You see, in 1 over G represents strength of gravitational force by background geometry, right? 1 over G. But this is strength of fluctuations on the background geometry. So these two compete here. So as a result, the notion of background geometry, in some sense, melt down, right? So my solution is, in some sense, breaking down at order 1, in some sense, right? Yeah. So maybe behind this system, quantum-gravitational effect already appears, right? So I'm sorry, Paimi. And so to understand this what I said more, and this I'm sorry, and this is the final one, and let's calculate entropy. Maybe, and this calculation is simple, and you can understand easily from the calculation I want to show. And suppose and our system like this, and we assume hydrodynamics approximation or just a local thermodynamics like this. And here, this is entropy density per volume. We use and the so-called Gibbs relation to estimate entropy density. And here, T, local temperature, assumed as Unruh temperature. Okay. And let's calculate. First, Unruh temperature. Alpha is acceleration. In my case, it is Unruh temperature. It is almost Planckian temperature. And now, and rho, what is rho? Rho is h by g and r square. And here, PR is like this. This is a radial pressure. And you can see this one cancel, and so, and 4 pi r square, and g eta, like, yes, I'm okay. And so entropy density is, just a moment. And 4 pi, 2 pi, like this. And cancel out something, eta cancel, and so 4 pi r square LSP 2 pi to sigma, like this. Okay, let's substitute it here. This gives you 4 pi dr r square. And this is, of course, contains GRR component here. So it is, and the GRR is this one. This is GRR. And the 4 pi r square cancels out. So like this. And eventually, we integrate from 0 to r, and this gives you cancel. This one. You see, and this is exactly area rho, right? Area rho, you see. So this result is quite suggestive, right? So from the beginning, we only consider just one pure state, right? However, in this way, according to thermodynamic law, and this guy has finite entropy, and the entropy exactly agree with entropy area rho, maybe, and this result tells you this zero state should be some macroscopic wave function of quantum gravitational degrees of freedom, right? Because, as I said, here, in this way, and our system already close to a part of a quantum gravitational regime, right? So, and intuitively like this. Here is semi-region. This is quantum gravity region. Here, energy scale is here, right? This connecting part is the place this ky metric living here like this. So in this sense, this ky metric should connect semi-classical gravity and the quantum gravity in this way. So, and of course, and some people don't believe this picture because, and this is already inside the bad region in this way. However, and quantum gravity physics should connect eventually semiclassical region. So here, this part should exist, right? So here, and some physics should play a role on the bridge, right? Bridge between them. So I think this KY metric is a kind of quantum gravitational phase, right? Macroscopic phase, and like this. So I think, and this view eventually gives some more dynamical or more fundamental picture between them. Okay. Thank you so much. Your time. Yes.
Two questions.
Thank you for your talk. And so in the beginning, from my understanding, in the beginning, you started with the outgoing light cone coordinates with U and R. And then that leads you to this self-consistent configuration. So I think this is related to some of the questions asked earlier. So I'm interested in, suppose I consider, instead of U and R, I started with a UV coordinate. And then that would allow me to consider both outgoing flux and ingoing negative flux. So I'm wondering, if I start with that metric ansatz from the beginning, am I able to, maybe after many complicated steps, am I able to arrive in the end to say that the Unruh vacuum could also be a self-consistent, non-perturbative state?
I don't know, and the point is, as I stressed, and to construct the candidate metric, you have to consider time evolution of the Bohr's collapsing matter and back reaction Bohr's in a finite time scale, right? As long as you can do, and you should be able to do that. I think so. Yes, this is my view. And I want to say, and this, as I said, and in the introduction, and this KY metric can be derived in many ways. And even if you don't assume outgoing Bayesian metric, you can get the same metric by another argument, like entropy maximization. So in this, yes. So in this sense, and this metric is quite universal, independent of the detail of the outside metric, right? So yeah.
I'm wondering if you think this is unique, that for spherically symmetric configuration, this is the only self-consistent solution.
Of that guy?
Yeah.
And for example, if you assume anomaly, G mu nu equal to anomaly, and metric G mu nu is independent of the total mass, right? Because maybe black hole structure should be universal, right? So let's assume total mass dependence disappear in the metric. And the final one is enough compact. Yes. This case, and anomaly satisfy at scale, this one. High energy regime, and in high energy regime, G mu nu equal to anomaly. These three conditions gives you KY. Yes. Yeah. So.
Do you still have to worry about the fact that if you try to make the black hole by a collapse process, in some frame, all the curvatures were low, and if you just have normal scalar fields as matter and no kind of non-locality or non-commutativity like beaming head, how would you trigger any new strong stress tensors because everything looks low? Is that a valid question? Is that something to worry about?
Okay, so, and suppose and you consider and collapsing object, right? And the point is the dynamics is 4D, not 2D, right? So in the 4D case, and as I said here, and energy can flow r direction and the theta direction both. So by using this one or Israel junction condition, and if your shell emitting radiation to the outside, and then automatically, as a result of the energy conservation, you have tangential pressure always. Such a tangential pressure can become large as the shell close to its own shell slit radius. And however, such largeness cannot be explained just the 2D dynamics. So as I said, 4D dynamics is required. And so this is one simple reason why and such large effect can appear. And I have shown that is true in this setup. Yes.
Okay, so let's thank Yuki, and we can have lunch.
Thank you so much for your time. Thank you.